So what if I told you there's a project out there claiming to have built an operating system kernel that's not just a bit smaller than Linux, but nearly 100 times smaller? Yeah, it's a massive claim. So today, let's just break it down and see what's really going on here.
Okay, let's just start with that number. A memory footprint 96 times smaller than a standard Linux kernel. We are talking about going from over 12 megabytes all the way down to less than 128 kilobytes. That isn't just an optimization, you know? That's a complete rethinking of what a kernel can even be. But that's just the first number.
And the claims? They don't stop there. This same project says it can respond to interrupt requests, those supercritical signals from your computer's hardware, over 4 times faster than Linux. In the world of high-performance computing, that kind of responsiveness, well, it's an absolute game changer.
Now, these are not hypothetical numbers. These are the actual benchmark claims of a new, and I gotta say, incredibly ambitious project. So, let's get to know the SEX microkernel.
Okay, so the name, SEX, it actually stands for Single Address Space Operating System. And this is a really key detail. See, unlike your traditional OS that gives every single program its own little virtual memory sandbox to play in, this design puts everything into one gigantic shared memory map. It relies on totally different methods for security, and it's a radical choice all aimed at one thing: raw performance.
And, the project's own description really doesn't pull any punches. It calls itself revolutionary, it makes a point of saying it's written in Rust, the modern systems language, and it spells out its 2 main goals: just raw, unadulterated performance and super strong hardware-enforced security.
So how on earth does it plan to deliver on these promises? Well, the secret sauce is this core philosophy that gets rid of something you find in pretty much every other modern operating system, and that's locks. Okay, so think of a normal kernel like a busy city grid full of traffic lights. Those lights, which programmers call mutexes or locks, are there to stop different processes from crashing into each other. But they also create huge traffic jams. This project's core idea, and you can see it right there in that first achievement, is to rip out every single one of those traffic lights. It is a completely lock-free design, basically creating a wide-open superhighway where data can just flow at max speed without ever having to stop.
So let's look at the architecture. Because if you're not using traditional memory separation and you're not using locks to keep things in order, how do you keep everything from just, crashing and burning? The whole design relies pretty heavily on some cool, modern CPU features.
The stack is it's remarkably simple. At the very bottom, you've got that tiny pure Rust microkernel, which they claim is less than 7,000 lines of code. Above that, you have your actual apps and services. And the security glue holding it all together? That's Intel MPK, or Memory Protection Keys. It's a hardware feature that lets the kernel basically assign security keys to different chunks of memory, preventing any program from touching stuff it isn't supposed to.
But does this really elegant minimalist design actually translate into those wild performance numbers we saw at the beginning? Well, the project's own documentation lays out a direct head-to-head comparison against a modern Linux kernel to make its case.
So the stage is set. In one corner, we have SEX OS version 1.0.0, and in the other, a standard, contemporary Linux 6.x kernel. Let's look at the numbers.
First up, inter-process communication, or how fast 2 programs can talk to each other. The benchmark claims SEGOS gets it done in just 340 CPU cycles, while Linux takes 1,200. That's a 3.5 times improvement. That's a massive speed up for any app that relies on fast communication.
Next, how much data can you actually pump through the system? For I/O throughput, the claim is a whopping 40 gigabytes per second, more than triple the 12 gigabytes per second they measured on the Linux baseline.
And this right here, this brilliantly illustrates that interrupt response claim we heard about earlier. The benchmark shows it responding in just 420 cycles, while Linux takes 1,800. That's that 4.2x faster reaction time we were talking about. A huge advantage for any system that needs to react to hardware events, like right now.
And finally, we come back to the most dramatic claim of them all, that memory footprint. This chart really just visualizes the insane difference between less than 128 kilobytes and over 12,000 kilobytes. It is a jaw-dropping 96-fold difference.
So when you look at the full summary table from their source material, the claims are just consistent and really impressive across the board. We're talking 3 to 4 times faster on key metrics and almost 2 orders of magnitude smaller. It really paints a picture of a radically efficient system. Now, those performance claims are definitely compelling, but when we start digging into the project's public source code repository, an interesting little detail pops up that adds a whole new layer to the story.
Remember this line from the project's description? It very, very clearly states the microkernel is written in Rust, a language that's famous for its memory safety and modern features, and that aligns perfectly with what the project's trying to do.
However, if you look at GitHub's automated language analysis of the entire project repository, well, it tells a bit of a different story. Rust, it turns out, accounts for just 2% of the code. The dominant language, by a massive margin, is C at nearly 86%.
This raises a fascinating question, right? And there are a few possibilities. One is that the written in Rust claim refers only to that tiny 7,000-line microkernel core, while all the other stuff around it, like drivers and system utilities, is in C for compatibility. Another idea is that the project is just in a long-term transition, slowly replacing C with Rust. Either way, it really highlights the huge challenge of building a modern OS and the practical trade-offs you have to make.
But you know what? Regardless of the language breakdown, the SEX microkernel project really forces us to think about the bigger picture. It's pushing this radical vision for OS design that basically throws out decades of conventional wisdom, all in the pursuit of raw performance. And it leaves us with a really compelling final thought. Could these bold, lock-free, single-address space designs actually be the future?